Okay, I've started recording. Let me go ahead and share the screen. Share. Here we go. Share content, screen number 1. Hopefully everybody can see the kitty cat. All right, great. All right, so let's go ahead and get started. So I'm gonna go ahead and do the whiteboard. I like this whiteboard. It's very similar to what we would have if we were actually face to face in person, believe it or not. You have not been in the chemistry classroom, but I had them put a board from one end of the classroom to the other end of the classroom. And you ever been in a I mean have you ever seen a movie where the professor is up in front of the classroom and it's completely filled with equations? Yeah, that's me. That's me. I actually had, they said when they hired me, they said, "Well, what do you want?" And I said, "I want a board from one end of the classroom to the other." And they're like, "Okay." All right, so here we go. So this whiteboard is similar to that, but I don't have quite the room. All right, let's go ahead and do chapter 8. Let's get started on it. Okay, so first off, when we talk, chapter 8 is about bonding. That's what chapter 8 is all about, is bonding, okay? And we want to join atoms. And when we join these atoms, we want to make big structures. And we'll make things bigger and bigger and bigger until you end up with, like, for instance, a person. You know, you are just basically a big membrane filled with 70% water and a bunch of chemicals floating around. That's what you are. And so, but holding together all this stuff that makes you are these things called bonds. Okay, and they're just the glue that holds stuff together. Now, we've already kind of went over this before. We have ionic bonding and we have covalent bonding. All right, an ionic is generally metal nonmetal or polyatomic ions. All right, that's generally what we've got there. Metal versus nonmetal or polyatomic ions. Okay, and covalent, we have nonmetals. Let me not get to the definition first. There we go. We have nonmetal. And this generally involves sharing electrons. Now, there are tons and tons of ionic compounds in this world, but really the more exciting stuff is going to be covalent compounds. Ionic compounds, generally we call them salts. So if you have an ionic compound, generally you call it a salt. All right, covalent's pretty much everything else. All right, now, kind of like to clean up some business here, we have something called the octet rule. And I have to be very careful how I write octet because I want to use a K for the C, which is the German spelling. You know, one of the hazards of learning foreign languages is sometimes they start to get scrambled up with each other. So sometimes I'm wanting to speak German when I'm speaking English, and sometimes I'm speaking English when I want to speak German. So it's just one of those things. So the octet rule with a C is atoms gain, lose, or share electrons to get a full valence shell. Now, this is a little bit different from what the text says. The text says actually 8 electrons, but actually you can get a full valence shell without there being 8 electrons. It doesn't have to be 8. It often is 8, but it doesn't have to be 8. Okay, now what do we mean by a full valence shell? Now, a full valence shell, generally when we say full valence shell, what we generally mean, though not always the case, is isoelectronic with a noble gas. That's what we really mean, is we're isoelectronic with a noble gas. What is iso? I used the fancy word this morning. I said isoelectronic. What does that mean? All it means is that you have the same number of electrons as a noble gas. That's all it really means. Okay? And if you have the same number of electrons as a noble gas, you also have the same electronic configuration, because electronic configuration is generally driven by how many electrons you have, not necessarily what it is. It's however, so if you have, for instance, and I have my periodic table today, if you have your periodic table, you'll see that argon has 18 electrons. And so if you end up with 18 electrons by either gaining, losing, or sharing, well, guess what? You're isoelectronic with argon, and you now have a full shell. Okay? That's what it means. All right. And so when we're making compounds, generally atoms want to have full valence shells, and that's what drives a lot of forming of bonds. Now, here comes the important stuff, and that is for ions, what happens? Okay, so when we form an ion, let's say we have chlorine, and it becomes an ion. And we should know by now that chlorine, when it becomes an ion, it becomes chlorine minus. Because if you recall, and this is where it's so important that we keep, that we stay on top of these things. If you recall from previous chapter, it goes +1, +2. We hop over the transition elements, goes +3, plus -4, -3, -2, -1. Remember that? That's the pattern, that if an element becomes an ion, that's generally the charge that it's going to have. So chlorine becomes chlorine -1. So if we were to look at chlorine, we would say chlorine would be the electronic configuration. And once again, we have our periodic table in front of us. We would say that chlorine would be what? We remember the rule for doing electronic configurations. We go left to right, top to bottom. We start with hydrogen and we go left to right. So if we start with row 1, for chlorine atom, we would say 1s, 1s2 for the first row. We would drop down to the second row. We'd say 1s2, 2p6, and then we drop down to the third row where chlorine is, and we would say 3s2, 3p5. There's our electronic configuration for chlorine. All right, it's a third row element. It's just S's and P's. Where are the valence electrons? The outermost. And these are your valence. And how many valence electrons do we have? We have 5. 7, I'm sorry. That's what I get for being early in the morning. We have 7. Okay, we have 7 valence electrons. And we can count across 2 because, well, this is element number 5A. That's 7A, sorry, 7A. And it has 7 valence electrons, okay? So it's the highest S's and P's. You got your 3s and your 3p. The 2s and the 1s don't count for valence electrons. The valence electrons on the outside. So let's take a look at chlorine ion. So chlorine ion, well, what does it mean to be chlorine ion? And the minus sign right here means an extra electron. That's what the minus means in the minus. In chlorine minus, it means you have an extra electron. So how many valence electrons do you have at this point? Really, you have 8, but let's see where it goes. And so if you have chlorine, well, you'd say 1s, 2, 2s2, 2p6, sure enough, for your core. And then you go 3s2, 3p. But if you're chlorine neutral, you would say chlorine neutral would be what? 3p5, right? But chlorine ion has an extra electron. Now here's the important part. Here's the important question. It's not just, well, we just add it in. There's more to it than that. But if you add an electron, it goes into the next open spot. Where's the next open spot? The next open spot is right here with the 3p5. I've got room for what? One more. It can hold a maximum of 6, so there is room. And so sure enough, it goes in as 3p6. Okay, so the chlorine ion would be 3s2, 3p6, sure enough. Okay, now it has valence electrons is 8. There we go, it has 8 valence electrons. Now, what has 8 valence electrons? Well, those would be your noble gases, except for helium. Remember what I said, the octet rule is get a full shell. Well, helium only has 2 valence electrons, so it doesn't have 8. But let me prove that to you. So let's go ahead and draw out argon, which would be the next one over from chlorine. Argon is 1s2, 2s2, 2p6. There's your first full shell is 2p6, which is neon. And then we drop down and we see 3s2, 3p6 for argon, and its valence electrons is 8. So argon has 8 valence electrons. What did chlorine just do? It is now, when it became an ion, what did it do? It gained or lost electrons to become isoelectronic, or a full shell with the noble gas. And it does have a full shell now, argon, and it does have the same number of electrons, and it is isoelectronic with your noble gas. There it is. Okay? And so similarly, when we lose electrons, we should lose electrons in the same sort of way. Now, let's say we have aluminum. Let me switch colors here. And aluminum is what? It's 1s, 1s2, 2s, 2s2. Aluminum is the second row element, so that's 2p, 1, 2, no, actually the third row element, so that's 2p6, 3s2, and 3p1. There's aluminum. So aluminum is 3p1. Okay? What does aluminum become when aluminum becomes an ion? Well, aluminum becomes aluminum 3+. Where are those ions going to come from? Well, they're going to come from the valence shell, which are these guys right here. And so we're going to pop off the P's, we're going to pop off the S's, and so you're going to end up with 1s2, 2s2, 2p6, and now we're missing 3 electrons, because what does 3 mean? 3 means, 3+ means missing 3 electrons. Where'd they come from? They came from the valence shell. All right. Now, who is this isoelectronic with? Well, 2p6 is neon. And so we say neon is 1s2, 2s2, 2p6, and it's isoelectronic. So how many valence electrons do we have up here? We have valence is 3 for aluminum, and down here the new shell, this is actually our new valence shell. This actually has 8 electrons, and this is our valence shell for neon, and now it has 8 valence electrons. It's a previous shell. Okay, so we have, in this case, we have lost 3 electrons off the aluminum to get a full valence shell. But look, and this can be a little hard to wrap our heads around. If you're looking at the periodic table, you say, wait a minute now, it lost 3. How can you have a full shell if you're losing? Well, you're going to the previous shell. Okay, and chlorine, we went to the next shell. We completed the shell with chlorine. With aluminum, we're going to the previous shell, and the previous shell is neon. All right, previous shell is neon. Now, wrap up this little conversation here. Unfortunately, it's always a one-sided conversation, but to wrap this up, what do we do about transition elements? Now, here is where it gets really interesting. So far right now, we just said, oh, well, we have our S's and P's. This is up to row 3 elements, and we say, we got your S's and P's. You either add them into the S's or the P's, or you take them away, and either way you go to a neon, or not a noble gas configuration. So what if we have something like iron? Iron, how do we do iron? Well, let's go ahead and just do a noble gas configuration. So we say iron, previous row for iron was what? Argon, core elements. And then we said 4s2. And then we go, remember the D's start with 3 for the first row of D's, and we say 3d6. All right. Now, valence electrons for your transition elements, it depends. It depends. And we're still not going to get into saying definitively how many valence electrons does a iron have. Depending on who you ask and what's going on, iron can have either 2 valence electrons, 3 valence electrons, 6 valence electrons. It just depends. All right, it just depends. We're not going to go down that rabbit hole, okay? But the question here is iron becomes iron 2 plus. We do know these two things happen. Iron goes 2 different flavors, right? We have iron 2 plus and iron 3 plus. I do know that. Now, regardless of where we say, whether we have 2 valence electrons, 3 valence electrons, or whatever, okay, one thing that we do know experimentally, and light and reality is all that matters. Okay, you can talk theory all you want, but reality is what matters. What's reality? Iron is 2 plus or 3 plus. That's the reality. So the reality is iron loses 2 electrons or 3 electrons. That's what it means to be 2 plus. That's what it means to be 3 plus, is you've lost 2 electrons or you've lost 3 electrons. Now, here's the thing. When we write out the electronic configuration for these guys, the rule is going to be you lose from highest sublevel, or the highest subshell. What's the highest subshell up there? Is it the 4s or is it the 3d? It's the 4s is the highest subshell, because what makes something higher or lower is that number. It's that primary quantum number. It's the 4 is higher than the 3. Now, you may say to yourself, and I get it, okay, you may be saying, this is what you're telling yourself? But wait, didn't the D's fill up last? Didn't we go 4s2 and we counted and we went 3d1, 3d2, 3d3, 3d4, 3d5, 3d6? Did we not do that when we were counting? And you would think, am I right? You would think that you would, if you filled it up last, then that would be the first one that you would lose. And yeah, I'm with you on that. It would make perfect sense, but that's not how way things work. The way things work experimentally is that the highest subshells are emptied first. We fill them up according to the periodic table because we're filling up element by element by element, right? When we're talking about losing or gaining electrons, it's with the same atom. We're not going to the next element over. We have the same atom. So adding or losing from the same atom is not the same thing as going left or right across the periodic table. Okay, it's not the same thing. So we're going to actually lose from the S's first. Then we'll lose from the D's. Okay, so we will actually lose from that. And so we would actually say 4s1, sorry, there's two of them, so that's 4s0, 3d6. We would actually lose from the S's first. Then we can go ahead and lose from the D's, 4s0, 3d5. So we can do that. So we can start losing from the D's because the previous shell from that would be the P's. Okay, it would be the 4 P's and I mean the 3 P's and the 3s. Okay, so we would actually lose right here, just like that. Okay, so generally, if you're going to lose ions, you're going to lose them from the S's first. All right, just kind of aside. Now, what does that matter for us in the grand scheme of things? Not a whole lot, but it is something that you need to be aware of. That if you're asked to produce the electronic configuration of iron 2 plus, you do not want to be that person that says, I got this, 3s2, 3d4. You do not want to be that person that says that. All right, because it's going to come off from the S's because they're the highest numbers. Okay, all right. All right, so we finished that. Alrighty, so now forming ionic compounds. Now, an ionic compound is not really a compound in the sense of it is some sort of molecule. Now, when we see something like this, we see sodium chloride, and I used to be guilty of this. When I was in your position, I would say, yes, the smallest possible component of my sodium chloride is a sodium chloride. There it is. You know, it's an NaCl. If I look into a sample of sodium chloride, I should see a bunch of NaCl's paired up, right? Does that make sense? I should see, you know, a bunch of these. This is what I should see. This is what I visualized when I was in your position. But this is not part of what is part of being a chemist and or taking chemistry is understanding what is real, what is not. Okay, so that's not what's going on when you have a sodium chloride crystal. When you have sodium chloride, what you really have is you have a sodium ion, little ball, like a little animal ball, you know, the balloon animals, yeah, parked next to a chlorine. There you go, and they're parked next to each other, like that. If you have a sodium and a chlorine next to each other, and what has happened is that you have totally ripped the electron completely off the sodium and put it onto the chlorine completely. Okay, this is what happens in ionic compounds. Now, it takes energy to remove that electron. You got to yank it off. It takes energy. And that's what's that called? That's called the ionization potential. All right, one of our trends. It's always endothermic ionization potential. It's always endothermic. It takes energy. And when the electron goes to the chlorine, that is electron affinity, EA, electron affinity, and it's mostly exothermic, but it can be endothermic depending. If you've noticed, the higher the negative number, the more exothermic it is, the more favorable it is. And chlorine really wants that electron. So electron being added to the chlorine is really exothermic. And so the endothermic, removing the electron off the sodium, your exothermic going on to the chlorine, and between the two, that's part of your bonding energy. Okay, so far so good. And as far as calculating these numbers, don't worry about it. You need to know it about on the level I'm telling you, which is it takes energy to yank it off. You get energy when you put it back on. I know there's a difference in energy. I don't care how much. If I need to know, I can go look it up. All right. Now, the amount of energy you get back is not the same as the amount of energy for the whole thing. And so there's another piece to this, and it's called the lattice energy. Now, before I get into the lattice energy, what is a lattice? A lattice is a structure. It's like if you have a garden lattice. What does a garden lattice look like? It's a bunch of strips that are all connected to each other, left to right. You just go and so forth, okay? Let me make sure that the meeting is unlocked, and it is. Okay, and so you have all these things coming together. And so with a sodium chloride, now remember what I showed you, it's not like the red X, right? It's not like the red X. Okay, so once we form these ions, we yanked off the electrons, we added them back on. Now they form a lattice, and so we have some sodiums with some chlorine. So far so good. You say, hey, this is what I knew already, right? But it's not like that. Okay, so now you have over here, you have maybe another sodium, and over here maybe you have another chlorine, and over here maybe you have a sodium there, and you have a chlorine there, and you have a, let's see, let me make sure I'm balanced here. You have a sodium plus there and a chlorine minus there, and it just keeps going in all directions. Okay, that's not an explosion. I'm just saying it's going in all directions. And it's also coming out of the board. It's also going in the board. This is just one layer, a bazillions of layers. All right, this is a sodium crystal. So what does this mean? What is holding these guys together in the first place? In a roundabout way, it's the pluses attracted to the minuses. Opposite charges attract. And so what do we have here? We have this sodium is attracted to that chlorine. Okay, well, it's also attracted at the same time to that chlorine. And it's also attracted at the same time to that chlorine. And this chlorine is also attracted to that sodium over here. But this chlorine's also attracted to that sodium and this sodium and that sodium and this sodium over here to this chlorine and that chlorine. Not only that, but if I put a chlorine out over here, even though it's further away, they're still attracted. And if I put a sodium like way out over here, this chlorine and that sodium are attracted to each other. Everybody is attracted to everybody. Not only that, but the repulsions are also there. So if we want to look at repulsions, this chlorine is repulsed by that chlorine right there. And this chlorine is repulsed by that one right there. And this one, these two repel each other right there. And so you have the sodiums and the chlorines are all attracted to each other. And the chlorines and sodiums are all repelled by each other. And so what you're hoping for is that the attractions are stronger than the repulsions, that you have more attractions than you have repulsion. In other words, there is a net attraction. Now, how do you get a net attraction out of all this? Because you'd say, and reasonably so, if you're thinking ahead on this, you would think that there's just as many sodium chloride attractions as there are sodium chlorine repulsions. Wouldn't you think there's just as many? If you giveth, you taketh, right? And that is true. But by the arrangement of the crystal, there are different arrangements. you can have actually different arrangements where you have the layers. Here's, oops, I meant to change colors here. Here's the second layer. You see how it fits over the holes in between each one? And then we can do another layer on top of that. Here's the third layer sitting on top. See the layers? I'm trying to color code. I'm trying to do a three-dimensional object with two-dimensional colors. All right. The arrangement of the crystals minimizes. You minimize repulsions. You minimize repulsions, maximize attractions. Okay? That's like chapter 15, chapter 16, something like that. If you go on to Gen Chem 2, there will be some crystal theory. Okay? But just keep in mind, that's what's going on. Okay? So when we have an ionic compound, there is no compound. It's a bunch of attractions and a bunch of repulsions all together. Okay, when we say sodium chloride, we say this is the smallest unit. That's what we're saying. We're saying that in reality, the crystal is like sodium 3 billion, chloride 3 billion. Okay, but what do? What's the rules for empirical formulas? We go by the least possible numbers, right? And so if you divide by 3 billion, you get sodium chloride, okay? But the actual thing that we call sodium chloride is the entire salt crystal. The salt crystal you can see, if you look underneath a microscope or with just a magnifying glass, you see these little cubes, right? Well, guess what? The ions on one face can see the ions on the other side of the face in a distance that you can actually see. Now, is it strong? No. Does it hardly matter? Hardly at all, okay? But it's there. It's there. Now, the equation that determines all of that is the energy. It's called the Coulombic attraction, is some constant called the Coulombic Coulombic constant. You have the charges of each one, and it's over the distance. Okay, it's Q1, Q2 over the distance. Okay, so now this is an important equation here. K, the Coulombic constant, you have the charge of one, the charge of the other over the distance separating them. Now, remember what I said? Everybody sees everybody, right? The guys next to each other, let's say, let me change colors here again. Let's say these two right here, these two sodium chlorides, well, this distance part is pretty small. And so since it's in the denominator, that makes that attraction important because the distance is small. Now, we should have figured this out just in a hand-waving sort of way. We should have said, oh, yeah, of course, if they're closer together, they're important. But here's why. It's because of the distance term. If you're close together, that term is small, so therefore the energy is higher. If you're further apart, the denominator gets bigger, therefore the energy gets smaller, so it becomes less important. So sure enough, in a crystal, a salt crystal, that guy right there versus this guy over here on the other edge, well, they see each other, but the D term is so big that it hardly matters. So it's the first and second neighbors that are pretty much the most important ones. All right, now this is something that with a little bit of calculus, since it's repeating, you can set up what are called power series, and you can actually calculate the energy pretty closely if you know the distances and you know the charges. You can actually do this relatively easy. All right, well, just a little pixie dust's worth of calculus. All right, see? That's why you're in calculus, so that you can calculate the things in chemistry. And you're in chemistry so that you'll have to have calculus. You see, it's like a yin and yang sort of thing, you know? And of course, the reasonable person would say, if I don't care about chemistry, why do I need calculus? Good point. All right, so now Here's the thing. Now I've explained where all this is coming from as far as all this goes. And so here we go. So let me write this down again. Let me go. We say E equals the Coulombic constant, charge 1, charge 2 over the distance. All right, we have this. This is just, let's just accept this for a second. This guy is a fraction, is it not? Isn't it a fraction? Yeah, it's got a top part, it's got a bottom part. Listen, guys and ladies, a lot of stuff is like this in science. It's one thing to memorize the formula, but it's another thing to look at the equation and say, you know what? What is it telling me? What is this equation telling me? It speaks to me. Now, I'm looking at this equation this morning, and this thing is talking to me. It does. It speaks to me, and it should speak to you. Especially, I didn't take my meds this morning. So, sure enough, the equation is speaking to me. And you know what it says? It says, Mr. Pierce, it says, if you increase the distances, I will get smaller. And if you decrease the distances, I will get bigger. But it's also telling me, it says, if you increase my charges, I will get bigger. And if you decrease my charges, I will get smaller. Do you see what I'm saying there? This is what I mean by equations. They should speak to you. Not just in chemistry, but in physics and calculus and whatever. This is how we get from level 1 understanding to level 2 understanding. Level 1 is where you just memorize the equations and hope like hell it shows up on the exam. Level 2 is you still memorize the equations and hope that they show up on the exam, but at least you understand what's going on. I got a question. Shouldn't D be D squared? And the answer is no. No, it's not. No, it's not. And it is a well-known equation. D squared, you're probably thinking about like gravity. I think gravity goes by the square of the distance, doesn't it? Doesn't gravity go by the square of the distance?
The force of electricity, or the fields, electrical fields.
Electrical fields, yes. But for this, it does not.
Okay.
It is linear with distance. I'm absolutely with you. And I think when we're talking about between fields, aren't we talking about between plates? Plus plate minus plate.
Yes.
It would be the force between them goes as proportional to what, the square of the distance.
Correct.
Right. And that's fields. Okay, and I'm with you. See, hey, look at that. I can remember some of my electromagnetic physics. How about that? First thing in the morning. But it's true. When we're talking electrical fields and we're looking at voltage and things like that, the way the math works out, it ends up being the square of the distance. It does. Okay. When we're talking about point and we're talking about the energy in between, not the force, the energy between is going to be so many joules, and it goes as the linear function. It's linear with distance. Okay, so it is linear. I suspect that there's some sort of integral going on here. If you take the integral minus infinity of x, what do you got? You got 1/2 x squared, right? And you get these square terms going in. Right, everybody remember that? Your calculus, you take x, the integral of x is 1/2 x squared. What's the integral of x cubed? It's, it's so forth, right? 1 over, what is that? 1 over, anyway, you take that power, drop it down. Okay, so that is a great question. They are related. They are related. The Coulombic constant versus the field strength and the distance between the two. They are related. They're not the same thing, but they are related. Okay? And I have to admit, the first time I saw this, Justin, the first time I saw this with the Coulombic and I had physics, And I said, wait a minute now, isn't that so supposed to be a square? And the answer is no. So your first instinct as a sciencey Padawan is that, it is going to be a square, but it's not. It's not. Okay. Okay. Great question. Great question. Let me erase this so we can move on here. But yeah, you know what? Part of being a sciencey sort of fella or lady, Mr. Justin, is to be able to pull together different disciplines and be able to make them fit. You see what I'm saying? That is a level, like I said, level 1, level 2. That's a level 10 sort of thing. If you can start pulling together stuff like that, that's when you can start saying things like, I think I really understand this stuff. That's when you can start saying things like that. You start pulling everything together. That's when you become a quote unquote educated person. Yeah. Imagine that. We're all going to be educated one day. All right. So we have this. Now, what are we going to do with this? Now, getting back to what I was trying to explain, the idea that these equations should speak to you, and sometimes they speak to you and say things like, oh, Mr. Justin, I'm supposed to be a square, ain't I? And it's like, shh, quiet. You're not supposed to be squared. You're just a D. You're just a D today. All right. And that's great, because they should talk to you like that. All right. Now, so D, as you increase D, you should decrease E. As you decrease D, you should increase E. As you increase the charges Q, Q1, Q2, you should increase E. And as you decrease Q, you should decrease E. All right. So what does that really mean? Now this is where it comes from when I say these things should talk to you. Let's put them in words. Let's give words to the equation. And the words would be, as Q increases, E increases. And 2, we should say, as D increases, E decreases. All right. Now, physically, we should also look at this as back to our example here, sodium and chlorine. Okay. All right. And this is related to what's called the lattice constant. This is where we're getting to it, lattice energy. By the way, this is not E is not the lattice energy, but it's related. All right, it's part of it. Okay, and we look at the sodium and chloride. What do we have here? Now, what do we have here? What we have here is what do we have? We have a plus and minus charge, right? But we also have a D between them. We have a distance between them, and we have 2 charges. Okay, we have 2 charges. And so that's what's feeding into this equation here, are these 2 charges are feeding in over here. Okay, so you got Q1 is 1, Q2 is minus 1. So the overall is minus. Energy's minus. That means it's exothermic, means it's favorable. Okay. And what's the D? Well, the D, you go in there and you measure, and it's so many nanometers. I don't know how many nanometers is off the top of my head. It's probably around 1.5 times 10 to the minus 10th meters. Okay, around 1/10 of a nanometer. Okay, but that's not important. We're not going to calculate the energy here. We're trying to get an idea of magnitudes, big versus small. Okay, we have this. Now, what do we know about this Q1, Q2? What do we know? One thing that we know about Q is that they are integers. Why is that important? What's an integer? An integer is like 1, 2, 3, 4. -1, -2, -3, -4. Those are integers, okay, right? That's what it means to be an integer, something I can count on my fingers with. Those charges have to be integers. We've never seen a chlorine -1/2. We've never seen an oxygen +3/4. Okay, it's always been O2-, chlorine-, aluminum 3+. It's always been integers for the charges, all right? This is important. Now, the distance, which is related to the atomic radius, what is the trend for atomic diameter or radius? As we go from left to right across the periodic table, they get smaller, right? Left to right, they get smaller. As we go top to bottom, they get bigger. Atomic diameters. Okay, how much is not important. But if you look on one of the charts, as we go across the periodic table with diameter or radius, as we go across R, and you know that 2R equals D, right? 2 radius is equal to diameter. Okay, so I'm kind of throwing them out, but they're proportional to each other. As you go across, sure enough, this is going across the periodic table. So we're going across, and this is R, okay? As we go across the periodic table, sure enough, it's getting smaller, but how much is R getting smaller? How much? And the answer is that when you go from here to there, and there to there, and there to there, it is not ×2 or ×3 smaller. And you may say to yourself, well, what does that matter? Well, if you go from, say, 1.5 to 1.4 to 1.3 to 1.2, what's happened? It's getting smaller, right? It is. But we're not getting smaller by a factor of 2 or a factor of 3. If we're changing charges to, say, if we're doing this, okay, where we have the 2 chlorines, what's happening to the charges there? They're going there. It's not 2 times, it's not 1 times 1, it's 2 times 1, right? That's a factor of 2. If we had like aluminum and chlorine, 3 chlorines, all right, we just went up by a factor of 3 with Q1, Q2. All right, so what does that mean? As these two are changing, this is the conclusion of this whole thing right here that I'm getting at. As one or both, one or the other changes, which one's most important? Just based on what you see here, based on this equation here, and based what you know about, Q1, Q2 versus D, which one do you think is going to be more important? The charge or the distance? I would think that the charges would be more important, because the charges go like 1, 2, 3, and 4, right? And I could have a -3 with a +3, and that would be 3 times 3, which would be 9. So the top part potentially is 9 times bigger than the bottom part. The bottom part's not going to change that much. It's going to change, but it's not going to change by a factor of 9. It's going to change by a factor of maybe 20%, not 900%. Do you see where I'm going with this? That given a choice between deciding if 2 things have changed, because this is one of these things. If you have 2 things that change, which one's most important? The charge or the actual size of the atoms? And the answer is the charge is the most important part. Okay, so what does this mean for us? So when trying to decide, so given same charges, in other words, we can go say lithium fluoride, sodium chloride, and let's go potassium bromide. Why not? These all have the same charges. These are all +1, -1. These are all the same charges. Given the same charges, smallest atoms equals highest lattice energy. Why is that? Because it's Q1. Someone trying to hold on just a second. I got a important text from my boss. First rule of dealing with bosses is answer the text. Okay. All right. First rule of dealing with bosses: always take care of the boss, right? as long as you want to keep your job. If you don't want to keep the job, then you don't. All right. So given these, that's a pro tip, by the way. Given the same charges, which one's going to have the highest lattice energy? It's the one that's going to have the smallest ions or the smallest atoms. Which one has the smallest atoms? This one right here, the lithium fluoride, has the smallest ions. How do I know it's the smallest ions? Because it's the furthest up the periodic table. Lithium is the furthest up on the left, and fluorine is furthest up on the right compared to sodium and potassium. So this would have the highest lattice energy. I'm just going to abbreviate that LE. And you look at potassium bromine, and so since it's the largest ions, it would have the lowest lattice energy. Now, usually when we're comparing things, remember what I said, the most important is going to be the charge. But usually when you're comparing things, you only change one thing at a time. So we're changing just the diameters or the radius. We're changing. All right, we're not changing charges. So given that, the same charges, smallest atoms, highest lattice energy. And conversely, we can do the same thing over here. And we can say, given about same R or radius or size, different charges, highest equals highest equals highest lattice energy, LE. Okay, so given a choice between sodium chloride, calcium chloride, and aluminum chloride, which one would have the highest lattice energy? Now, the size of these atoms are relatively close together. Sodium, calcium, and we could even go with magnesium if you'd like. Let's change that to magnesium just to keep it all on the same row. Sodium, magnesium, aluminum. So their sodium, magnesium, aluminum are more or less parked next to each other. So they're about the same size, sodium, magnesium, and aluminum. But what do we have here? We have chlorine, the same chlorine, but we have +1 here, -1 there. We have +1 here, -2, +2, -1 all the way down, +3, -1 all the way down. okay? And so now the Q part is Q1, Q2 is Q1, Q2 is -1, -2, and -3. So this one by far highest LE. Now the previous example on the previous page, when I said highest LE, they were different. And sure enough, the smallest radius was the largest, but the difference in energy you're going to see was not humongous. But sure enough, there was a highest and lowest. Here, it's about 3 times bigger. This thing right here is times 3 compared to this guy up here. Huge difference, as opposed to the previous page, which is right over here. Over here, sure enough, the lithium fluoride was a higher lattice energy, but what's the difference in radiuses between these guys? They're different. It is bigger, but it certainly was not a factor of 3, which we had over here. Look at that, factor of 3. All right, now, hold on to that thought for just a second. And so, let's see, what do we got here? I'm looking at the time. I'm going over on time. I promise I'll finish soon. We'll take a break, I guess, or maybe we can just keep driving on because I need to finish this thought, all right? And so, look, keep in mind what I just showed you in a hand-waving sort of way, okay? Hand-waving means I look at the formula, the equation speaks to me, right? The equation speaks to me. All right, we're going to let the equation speak to us. Now let's look at the data. Let's take a look at the data now. Let me pull this up. Where's my PowerPoint? There it is. Y'all see the PowerPoint? Yes or no? You do? Okay, good. Okay, there's my E, right? There's my coulombic attraction. Q1, Q2 over D, right? It's supposed to speak to me. Here's the data. Here is the data. Whoa, shoot. Hold on. Never mind me. And never mind me on that. Okay, here it is. Here's the data. So we're going to blow up this, and we'll try to blow it up so we can see it a little bit better. Okay, there's my numbers. Okay. All right, so here is the experimental data for lattice energy. And if you look down, let me review. I'm going to put inking. And if you look down this list here, these are all +1, -1. And look how these are bigger as we go down. Y'all see that? It is bigger as we go down the list. You see that? So lithium fluoride, those are the smallest ions, and cesium chloride is really big. You see that? Look what happens to the energy as we go down. As we increase D, what happens to E? It gets smaller. Lithium fluoride, small ions, close together, high energy. You got 1,030 kilojoules. Cesium is a pretty big atom. It's way down on the periodic table. All right. Cesium is still +1, right? And sure enough, the energy is smaller. Now, it's not twice as much smaller, though, right? It is smaller. Everybody see that table? You do see the table, right? Okay. All right, because I see some puzzled looks here. Are you seeing the same thing I see? See that number? See that number? See that compound? See that compound? All right, this is because Q1, Q2 over D, that's this part right here. Now, look left to right, though. Ew, look left to right. Check out this. You see SCN, right? Scandinavian nitride, SC, and SC is a +3. This is +3. This is -3. Look at this. they're not that much bigger. Hell, I mean, look, got nitrogen. Nitrogen is what? It's a second row element right there with fluorine. See, fluorine is second row element. Look at the difference between these two. What's driving that? What's driving this right here is being driven by that part right there. You see that? The sizes aren't that much difference, but what really is different is those charges. Look at the difference. 900-ish, 600 to 1,000, 900-ish versus nearly 8,000 because of the charges. So the lattice energy for SCN is huge compared to LiF or cesium chloride. Okay, even if you get up over here, this is a +2 -1 situation right there. Well, look at this. Look at the difference. You see that? It's about twice. +2 versus +2 times -1 is -2 versus +1 times -1 gives you -1. It should be about twice. If you just ignore the D term, D as in dog, the denominator. If you ignore the D term, what do you see? It should be about twice. What is it? It's about twice. You know what? Rarely do things work this well in science and chemistry where you can look at a formula, look at some data, and say, I get it. Now, I look at this data and I look at the formula and I say, you know what? I get this. Do you get it? Do you get it? Do you see what's going on with the numbers? This is what you go out and do experimentally, and then you say, I understand what's going on. It's the Coulombic attraction is what it is. All right, now there's other stuff going on. There's the energy going in, the energy coming out. You know, you got electrons being ripped off. You got electrons being added on. You know, there's energy, you giveth and taketh energy there, but you also have the lattice energy. And there it is. There is the lattice energy. Okay. There it is, guys. There it is, ladies. Do you see it? To me, this is beauty. This is beautiful. All right. This is the way things are supposed to work in nature. All right. It actually works the way that you think it should, or at least the way I think it should. It works. It works. Okay. All right. So let's see. We did electron configurations. We did the bowline. We did, let's see, we need polarity, Lewis structures. Tell you what, the next topic that we would cover here, we don't want to save here. The next topic would be Lewis dots and Lewis dot structures. Okay. That is something that I would like to be able to just do in one discussion. In other words, I want to start with the Lewis dots and work you all the way through structures and everything. And that's like a 2-hour thing. All right. So I think that what we can do is go ahead and cut it off today at this point, if that's okay with everyone. Okay. Look, there is stuff due tomorrow. I think there's a lab due tomorrow, right? And I'm going to get these labs that y'all turned in graded. By the way, they're looking pretty good. I'll get them graded today, the labs that you did. I think, what is it, 7 and 8 or something like that? Okay, I'll get those graded, no problem. And make sure you get the stuff due tomorrow. I think that is a Hess's Law experiment for tomorrow. Hell, I mean, you know how to do this. I mean, it's simple manipulation. You know, you get them to add up. Well, you know, you use heat equation, blah, blah, blah. No big deal. All right. You can always run these things by me. And by the way, yes, guess what yesterday was? Yesterday was the last day to drop. And so now you are committed. It's kind of like, y'all ever heard the joke, you know, the pig versus the egg at breakfast, right? You ever heard that? Pig, you know, the pig and an egg, a pig and a chicken. Let me put it that way. What's the difference between a pig and a chicken at breakfast? The chicken is involved. The pig is committed. Think about it, you know, the chicken produces an egg, the pig is the bacon, right? Pig's committed. So anyway, you're committed. So everybody's committed now. And so having said that, if you happen to miss an assignment like a homework or a lab or something, let's say you overslept or something, please get with me right away so we can figure out something to do. If you happen to miss something, please don't miss assignments. But if you do, get with me. All right, just get with me. We'll figure something out. All right. Okay, so having said that, we'll cut it off right here. I'm gonna hit stop, stop,